When installing a service grounding conductor within a rigid conduit, electrical codes mandate that the conductor be bonded to the conduit at both ends. This requirement ensures electrical continuity and provides a lower impedance path for fault currents to return to the source, thereby facilitating the operation of overcurrent protective devices such as circuit breakers or fuses. The purpose of this bonding is to minimize voltage differences between the conduit and the grounding conductor, which can occur during fault conditions. The bonding process involves creating a secure electrical connection between the grounding conductor and the metal conduit. This is typically achieved using bonding jumpers and appropriate fittings designed for this purpose. The specific requirements for bonding are detailed in the National Electrical Code, specifically Article 250, which covers grounding and bonding. In situations where the rigid conduit containing the service grounding conductor is installed underground, the bonding fittings used must be specifically rated for direct burial. This is because underground environments present unique challenges to electrical connections, including exposure to moisture, corrosive soils, and mechanical stress. Standard bonding fittings that are not designed for direct burial may corrode or degrade over time, leading to a loss of electrical continuity and potentially compromising the effectiveness of the grounding system. Direct burial rated bonding fittings are constructed for materials that are resistant to corrosion and are designed to withstand the mechanical stresses associated with underground installation. These fittings typically feature a robust design and are often made from materials such as bronze, stainless steel, or other corrosion-resistant alloys. They are also often sealed to prevent moisture from entering the connection. Several manufacturers offer direct burial-rated bonding fittings. Hubbell is one such manufacturer, providing a range of fittings specifically designed for this application. These fittings are typically listed and labeled by a recognized testing laboratory, such as Underwriters Laboratories, to ensure that they meet the applicable safety standards and performance requirements. When selecting a direct burial-rated bonding fitting, it is essential to consider the specific requirements of the installation, including the size of the conduit, the size of the grounding conductor, and the soil conditions. The fitting should be properly sized and rated for the intended application and should be installed in accordance with the manufacturer's instructions and the applicable electrical codes. In addition to using direct burial-rated bonding fittings, it is also important to ensure that the grounding conductor itself is suitable for direct burial. Grounding conductors used in underground applications should be made from materials that are resistant to corrosion, such as copper or copper-clad steel. The conductor should also be properly insulated to prevent it from coming into contact with the soil or other conductive materials. The National Electrical Code provides specific requirements for the size and type of grounding conductors used in various applications. These requirements are based on the size of the service entrance conductors and the type of grounding system used. The NEC also specifies the methods for installing grounding conductors, including the minimum burial depth and the requirements for protecting the conductor from physical damage. When installing a service grounding conductor in rigid conduit underground, it is essential to follow all applicable electrical codes and manufacturer's instructions. This will help to ensure that the grounding system is properly installed and that it will provide effective protection against electrical hazards. Ignoring these requirements can lead to dangerous conditions, including electric shock, fire, and equipment damage. The importance of proper grounding and bonding cannot be overemphasized. A properly installed grounding system is essential for protecting people and property from electrical hazards. It provides a low impedance path for fault currents to return to the source, which helps to ensure that overcurrent protective devices will operate quickly and effectively. It also helps to minimize voltage differences between conductive surfaces, which can reduce the risk of electric shock. In addition to the requirements for direct burial-rated bonding fittings and grounding conductors, there are other important considerations for installing service grounding conductors in rigid conduit underground. One such consideration is the need to protect the conduit from corrosion. Underground environments can be highly corrosive, and metal conduits can corrode over time if they are not properly protected. To prevent corrosion, the conduit should be coated with a corrosion-resistant material such as epoxy or polyurethane. The conduit should also be properly supported to prevent it from coming into contact with the soil. Another consideration is the need to protect the conduit from physical damage. Underground conduits can be damaged by digging, construction activities, or other mechanical stresses. To protect the conduit from physical damage, it should be buried at a sufficient depth and should be protected by a layer of sand or gravel. The conduit should also be marked to indicate its location. The NEC provides specific requirements for the burial depth and protection of underground conduits. These requirements are based on the type of conduit and the type of soil. The NEC also specifies the methods for marking underground conduits. When installing a service grounding conductor in rigid conduit underground, it is essential to follow all applicable codes and standards. This will help to ensure that the grounding system is properly installed and that it will provide effective protection against electrical hazards. Ignoring these requirements can lead to dangerous conditions, including electric shock, fire, and equipment damage. Grounding and bonding are critical aspects of electrical safety. Proper grounding and bonding practices are essential for protecting people and property from electrical hazards. These practices help to ensure that electrical equipment is properly grounded and that fault currents can safely return to the source. This helps to prevent electric shock, fire, and equipment damage. The NEC provides comprehensive requirements for grounding and bonding. These requirements are based on years of experience and research and are designed to ensure the safety of electrical systems. It is essential for electrical professionals to be familiar with these requirements and to follow them carefully when installing and maintaining electrical systems. In addition to the NEC requirements, there are also other codes and standards that may be applicable to grounding and bonding. These include local building codes, industry standards, and manufacturer's instructions. It is important to be familiar with all applicable codes and standards and to follow them carefully when working with electrical systems. Grounding and bonding are complex topics, and there is always something new to learn. It is important for electrical professionals to stay up to date on the latest codes, standards, and technologies. This will help them to ensure that they are providing the safest and most effective electrical systems possible. The correct size of the grounding electrode conductor is critical for electrical safety. The size of the grounding electrode conductor is determined by the size of the service entrance conductors. The NEC provides tables that specify the minimum size of the grounding electrode conductor based on the size of the service entrance conductors. It is important to use the correct size grounding electrode conductor to ensure that the grounding system can effectively carry fault currents back to the source. Using a grounding electrode conductor that is too small can result in a dangerous situation. If a fault occurs, the grounding electrode conductor may not be able to carry the fault current, which can lead to overheating and potentially a fire. It is always better to err on the side of caution and use a grounding electrode conductor that is slightly larger than required. The type of grounding electrode is also important. The NEC recognizes several different types of grounding electrodes, including ground rods, ground plates, and metal underground water pipes. The type of grounding electrode that is used will depend on the specific situation. In general, ground rods are the most common type of grounding electrode. Ground rods are typically made of copper or copper-clad steel and are driven into the ground. Ground plates are typically made of copper and are buried in the ground. Metal underground water pipes can also be used as grounding electrodes, but they must meet certain requirements. The grounding electrode must be in contact with the earth. This means that the grounding electrode must be buried in the ground or in contact with a metal underground water pipe. The grounding electrode must also be located as close as possible to the service entrance. This will help to ensure that the grounding system is as effective as possible. The grounding electrode conductor must be securely connected to the grounding electrode. This is typically done using a clamp or other fitting. The connection must be tight and corrosion resistant to ensure that it will last for many years. The grounding electrode conductor must be protected from physical damage. This can be done by running the grounding electrode conductor in conduit or by burying it underground. The grounding electrode conductor must also be accessible for inspection and maintenance. It is important to periodically inspect the grounding electrode conductor to ensure that it is in good condition and that the connections are tight. If the grounding electrode conductor is damaged or corroded, it must be replaced. The grounding system is a critical part of the electrical system. A properly installed and maintained grounding system can help to protect people and property from electrical hazards. It is important to follow all applicable codes and standards when installing and maintaining a grounding system. In addition to the grounding electrode conductor, there are other important components of the grounding system. These include the main bonding jumper, the equipment grounding conductors, and the grounding electrode system. The main bonding jumper is a conductor that connects the neutral conductor to the equipment grounding conductors at the service entrance. The equipment grounding conductors are conductors that connect the metal parts of electrical equipment to the grounding system. The grounding electrode system is the system of grounding electrodes that are used to connect the electrical system to the earth. All of these components must be properly installed and maintained to ensure that the grounding system is effective. The purpose of grounding is to provide a low impedance path for fault currents to return to the source. This allows the overcurrent protective devices, such as circuit breakers and fuses, to quickly trip and clear the fault. Grounding also helps to minimize voltage differences between conductive surfaces, which can reduce the risk of electric shock. Bonding is the process of connecting together all of the metal parts of an electrical system. This includes the metal conduit, the metal enclosures, and the metal equipment. Bonding helps to create a low impedance path for fault currents to return to the source. Bonding also helps to minimize voltage differences between conductive surfaces, which can reduce the risk of electric shock. Grounding and bonding are essential for electrical safety. Proper grounding and bonding practices can help to protect people and property from electrical hazards. It is important to follow all applicable codes and standards when installing and maintaining electrical systems.